Hi, welcome back. We're going to be having a look at register operations, particularly how to do bitwise operations with registers. We've got our program running. Let's just make sure it's still running okay. Just flashing our LED, there we go. So we'll stop that and we'll just have a look. This line, set LED 0, what does it actually mean? Well, it's a macro for this piece of code here. So we can type that piece of code in instead, and we can watch it run. Okay, but what does that line of code actually do? Well, first of all, that line of code can be written as port B equals port B bitwise OR with 1 shifted left PB5 times. So that's the equivalent code there. So we can actually run that code and it will work. However, what does this 1 shift left mean? Well, that's port B equals port B bitwise OR with 1 shifted left 5 times. So that's PB5 is also a macro for 5, and you'll find those sort of macros are pointed to by this IO file. In fact, it's within that is a pointer to the one for the 3 to 8, where you'll actually find things like port B5 are initialized. So what does this mean? Port B, bitwise OR with 1 shifted left 5 times. So if we thought of a byte type number, which was 1, 2, 3, 4, 5, 6, 7, 8 bits, and the first thing we did was put a 1 there, and then we shifted it left 5 times, then it would be doing this sort of operation. So we would end up with this, and it would be in bit 5, which of course is the 6th bit. This is bit 0, 1, 2, 3, 4. I've got too many in here. There we go. That's why we don't write like this, because it's really hard to get it exact. So now we have 8 bits, and it is 0, 1, 2, 3, 4, 5 here. So just double check that it is bit 5, the 6th bit. Of course, that means that there are 2 to the other side of it. So that code there is exactly the same. So let's run that and see if it works. There we go, it's working. Pause that, step it through. That line there turns it on. So what does this line actually do? Well, we always read code, we work out what this side is doing, and then put it into that side. So port B is ORed with this number here. Now when you OR something, we're forcing bit 5 high. And that's the effect of ORing something with a 1. Of course, we don't just want to force bit 5 high, we want to leave unchanged. And of course, if we OR something with a 0, then it stays with its existing form. Now, clear LED is similar but different process. Here's the code for a clear LED. And so what does this do? Well, again, we will unpack this. So port B equals port B and that. And if we copy and paste this, we can unpack this. We know what this stands for. And this means the inverse, which means we can put two ones there, a 0, and the ones there. So that's what that code is doing. It's ANDing, bitwise AND. Each bit in port B is bitwise AND with this. And of course, forces bit 5 low. And what we want to do, of course, is leave the rest unchanged. Unchanged. So this is what our code is actually doing. Run that. And there's our LED flashing on and off. So what is this thing, port B? Well, it's a register. It's inside the edge of the microcontroller. So if we had a look at this diagram, for instance, inside our microcontroller, and here's outside our microcontroller, you'll find there's an 8-bit register here. And it's connected to the data bus, which is 8 parallel wires. So each one of these is fed off one wire of the data bus. And then when we want whatever's on the output here to be available to the pin, we enable these little buffers for it to go through. Now, you'd be familiar with perhaps the clock input here. These are not always clocked. These are only clocked when we want a signal to be stored into the register, rather than a normal register clock which is going all the time. So when we want a 1 here, the data bus puts the 1 on here, clocks it through to the output, and then enables this one here for it to go through. At the moment, of course, all of these are enabled apart from B7, which is an input. So this is not enabled on B7 because B7 has got our little switch on it, but the rest of them are all enabled. The microcontroller bus, when it is active, of course, the signal's only clocked through when we want it to be clocked through, and then it only makes it to the output when we want to make it to the output. And we did that earlier in our program. We set it up here so that port B, all of these buffers were turned on so that the signals would go through, and then we turned off one of them. We turned that one off with this line of code here. And that's because it's connected to another register called the data direction register. So a microcontroller has a register for port, a data direction register, another set of these, another register, 8 bits, called the data direction register, and then it has a pin register as well, because this register is only for doing outputs. It's not an input register. So we need another register for that. If you have a look in the data sheet for the Atmel microcontroller, you'll find that it looks like this. So let's have a look. Here is our output register. And when we clock the signal through, it goes onto this line. However, it can't go any further until we tell it that it can. And so the data direction register, it makes this possible to connect that through to the output line. So we'll have our little LED here, and when we write into the port register, if the data direction register is allowing signals to go through this buffer, then that signal that we put into the register will find its way through to the output pin. Okay. So we've looked at a little bit of bitwise arithmetic. Remember, a port is 8 bits, so if we're going to OR it or AND it with anything, we need to do all 8 bits. And this line here is, this little shortcut is very common in C. We unpack that into this. That's a very common contraction in C. You'll see that everywhere. That's what it means. Now I hope you understand just a little bit more about how this code works. Of course, we don't often write this sort of code. There's a reason we write this sort of code, and that is because getting our ones and zeros correct is extremely difficult and very confusing. So that's why we write this. Makes our programs much easier to understand. Hope that made sense to you. Cheers.